Cameras are essential devices that capture images of our world, from life's precious moments to the simple beauty of nature. But have you ever wondered how a camera actually works? In this Brainwaves video, we will explore the fascinating inner workings of cameras and how they transform the real world into digital images. Learn about the intricate processes of lenses, sensors, shutters, and algorithms that work together to create the images we see today. Join us as we take a deep dive into the world of photography and uncover the secrets of how cameras work. To understand how cameras work, we must first understand how they capture light. The light that we see in the real world enters the camera through the lens, which is a series of convex glass elements that refract and focus the light onto an image sensor. This sensor can be either a CCD or a CMOS sensor, and it essentially records the image by converting the light into an electrical signal. Once the light is converted to an electrical signal, it can be stored on a memory card or external storage device to be processed and displayed later. In the next section, we will explore the role of lenses in controlling the light that enters the camera. Lenses are a crucial component of any camera, and they play a key role in controlling the light that enters the camera. Convex glass elements in the lens cause the light entering the lens to converge, meaning that they are brought closer together. This is what allows the camera to create a focused image of the world around us. By adjusting the distance between the lens and the image sensor, the camera creates a sharper or softer image. The aperture in the lens also plays an important role in controlling the amount of light that enters the camera, by adjusting the size of the opening. Smaller apertures allow less light to enter the camera, and create deeper depth of field, while larger apertures allow more light to enter the camera and create shallower depth of field. In the next section, we will explore in more detail how aperture affects the amount of light that enters the camera. The aperture in the camera lens controls the amount of light that enters the camera. It is essentially a small circular opening within the lens that determines how much light is allowed to pass through to the image sensor. The size of the aperture is measured in f-stops, which are represented by numbers such as f1.8 or f22. A smaller f-stop value such as f1.8 corresponds to a larger aperture, which in turn allows more light to enter the camera. Conversely, a larger f-stop value such as f22 corresponds to a smaller aperture, which allows less light to enter the camera. Changing the aperture setting also affects the depth of field in the image, with a lower f-stop value producing a shallower depth of field and a higher f-stop value producing a deeper depth of field. By adjusting the aperture, photographers can control both the exposure and depth of field of the image. The image sensor is one of the most important components of a camera, as it is responsible for capturing and converting light into an electrical signal that is stored as a digital image. Image sensors can be either CMOS or CCD, and both technologies serve the same purpose. However, they differ in their structure and how they process images. The image sensor consists of millions of tiny photodiodes, which are essentially light detectors. When light hits these photodiodes, they generate an electrical charge that corresponds to the amount of light that was received. These electrical signals are then processed by the camera to create a digital image. In the next section, we will explore how CMOS sensors capture images and how the process differs from CCD sensors. CMOS, complementary metal oxide semiconductor, sensors are the more common types of image sensors found in modern digital cameras and smartphones. They are made up of millions of tiny photodiodes, as well as transistors and other electronic components that function to convert the electrical signal from the photodiodes into a digital image. The process of image capture begins when light hits the photodiodes in the image sensor. The photodiodes generate an electrical charge that corresponds to the intensity of the light they receive. The transistors then read the charge from each pixel and convert it into a voltage, which is then amplified and converted into a digital signal that can be stored as a digital image. In general, CMOS sensors are faster and more power efficient than CCD sensors, although they tend to produce more noise in low light conditions. In the next section, we will explore how CCD sensors capture images and how the process differs from CMOS sensors. CCD, charge-coupled device, sensors were once the standard image sensors in digital cameras, but have now been largely overtaken by CMOS sensors. They work in a slightly different way to CMOS sensors, but the general principles are the same. In a CCD sensor, light hits an array of photodiodes, which then generate an electrical charge that is transferred to a storage node via a series of capacitive gates. The charges from all the photodiodes are then shifted out of the sensor and converted into a digital signal that can be stored as an image. CCD sensors tend to produce better image quality in low light conditions and have a more uniform response to light than CMOS sensors. However, they are generally slower and less power efficient. As CCD sensors become less common and more expensive, they are mostly found in specialized applications where their unique properties are required. The electrical signal produced by the image sensor is an analog signal, which is a continuous signal that varies in strength and amplitude. In order to store this signal digitally, it needs to be converted into a series of discrete values that can be stored as digital data. This is where the analog to digital converter, ADC, comes in. The ADC is a piece of hardware that takes in the analog signal as input and produces a digital signal as output. The ADC essentially samples the analog signal at a specific frequency, and quantizes the amplitude of each sample into a set of discrete values. These values are then combined to form a digital representation of the original analog signal, which can be stored on a memory card or other storage device. In the next section, we will explore how the ADC performs this conversion process in more detail. The ADC converts the analog electrical signal into digital data by a process called sampling and quantization. Sampling involves taking measurements of the analog signal at regular intervals, and quantization involves assigning a numerical value to each sample based on its amplitude. The rate at which the analog signal is sampled by the ADC is referred to as the sampling frequency, and is measured in Hz, Hz. The higher the sampling frequency, the more accurately the ADC can capture the original analog signal. The quantization process assigns a specific value to each sample based on its amplitude. The range of possible values is determined by the bit depth of the ADC, which specifies how many bits are used to represent each sample. For example, an 8-bit ADC can represent each sample with one of 256 possible values, while a 16-bit ADC can represent each sample with one of 65,536 possible values. Once the ADC has converted the electrical signal into digital data, the resulting digital image can be stored on a memory card or other storage device. The data is typically stored in a format such as JPEG, RAW, or TIFF, which contains all the information needed to recreate the image. When a memory card is inserted into a camera, the camera's software system checks for the presence of a memory card and verifies that it is properly formatted. If the memory card is compatible and free of errors, the camera is able to write the digital image data to the card. The size of the digital image file depends on several factors, including the resolution of the image, the bit depth of the ADC, and the file format used to store the image. Once the image is successfully stored on the memory card, it can be transferred to a computer or other device for viewing, editing, or sharing. The camera shutter is a physical mechanism that controls the amount of time that light is able to enter the camera sensor. It works by opening and closing a curtain that covers the sensor, allowing light to pass through for a specified amount of time. The length of time that the shutter remains open is known as the shutter speed, and is measured in seconds or fractions of a second. Fast shutter speeds allow for a shorter exposure time, while slower shutter speeds allow for a longer exposure time. This affects how much light reaches the sensor and therefore affects the brightness of your image. In the next section, we will explore how the shutter speed affects image brightness and sharpness. The length of time that the camera shutter is open affects both the brightness and sharpness of the resulting image. When the shutter is open for a longer period of time, more light is able to reach the sensor, resulting in a brighter image. This is useful for situations where you need to capture an image in low light conditions, but a longer shutter speed also increases the likelihood of camera shake and motion blur due to any movement of the camera or subject. On the other hand, short shutter speeds can freeze motion and create a sharp image, but may result in an underexposed image if there is not enough light. The shutter speed can also be used creatively to achieve special effects, such as blurring motion or creating a sense of movement. In the next section, we will explore how the shutter speed can be balanced with other exposure settings to achieve the desired exposure. In order to achieve the desired exposure of an image, you need to ensure that the right amount of light is reaching the sensor. This involves balancing the shutter speed with two other exposure settings, aperture and ISO. Aperture refers to the size of the opening in the lens that allows light to enter the camera, and is measured in f-stops. A smaller f-stop number corresponds to a larger opening and allows more light to enter the camera. ISO refers to the sensitivity of the camera sensor to light, with higher ISO values making the sensor more sensitive and the resulting image brighter. However, higher ISO values can also introduce noise and reduce image quality. By adjusting the shutter speed, aperture, and ISO, you can balance these settings to achieve the desired exposure for your image. For example, you can use a fast shutter speed to freeze motion, a wide aperture to blur the background, and a low ISO to avoid noise in the image. In the next section, we will discuss some practical tips for adjusting these settings to capture the perfect image. After the image has been captured and stored digitally, it goes through a process called post-processing, which involves applying various algorithms to improve the quality and appearance of the image. These algorithms can enhance the color, sharpness, contrast, and other aspects of the image to make it more visually appealing. Post-processing can be done in camera or using specialized software on a computer. Many cameras come equipped with in-camera settings that allow users to adjust properties like contrast, saturation, and sharpness, while more advanced post-processing can be done using software like Adobe Photoshop or Lightroom. While post-processing can improve the quality of an image, it's important to avoid over-processing the image, which can result in unnatural and artificial-looking results. In the next section, we will explore some of the algorithms used in post-processing to improve image quality. There are several algorithms commonly used in post-processing to improve the quality and appearance of digital images. One of the most commonly used algorithms is the white balance tool, which adjusts the temperature and tint of the image to improve its color accuracy. Another common algorithm is the clarity tool, which adjusts the edge contrast to give the image more definition and sharpness. The sharpening tool is used to enhance the sharpness and detail in an image. The contrast tool is used to adjust the difference between the light and dark areas of the image. Other algorithms include the vibrance tool, which enhances the intensity of the image's colors without oversaturating them, and the saturation tool, which increases or decreases the intensity of all colors in the image. With these algorithms, photographers can fine-tune their digital images to achieve the desired visual effect. In the final section, we will explore how digital images are displayed and exported from the camera. After the post-processing of the digital image is complete, the final image can be displayed on the camera's LCD screen for review. This allows photographers to quickly assess the quality and composition of the image and make any necessary adjustments. In addition to displaying images on the camera, they can also be exported to external devices such as computers, smartphones, or tablets. The most common way to export images is through a memory card, which can be inserted into a card reader or directly into the computer. Some cameras also support Wi-Fi or Bluetooth connectivity, allowing for wireless transfer to other devices. Once the image is on a computer or other external device, it can be further edited or shared on social media or other platforms. In conclusion, from the initial capture of light through the camera lens, to the conversion of an analog signal into digital data, and finally to the post-processing and displaying of the final image, cameras are complex devices that have revolutionized how we capture and share visual experiences. In conclusion, we hope this video has illuminated the inner workings of cameras and how they have revolutionized the world of photography. With the advancement of technology, cameras have become more sophisticated, compact, and accessible, allowing people to capture and share their experiences and stories with just a click. And as we continue to innovate and push the boundaries of what is possible, who knows what exciting developments in the world of photography the future holds. Thank you for watching this Brainwaves video, and as always, keep exploring.